Hi everyone, this is Mrs. J, and today we're going to talk about segment relationships in circles. So first, we're going to learn about what's called the chord theorem. So this states if two chords intersect inside a circle, and just a reminder, a chord is a segment where both endpoints are on your circle, then the products of the lengths of the segments of the chord are equal. So first, let's dissect this together. So we have two chords that have to intersect inside the circle. So CD and AB intersect at point E. So that part is true. It says the products of the lengths of the segments are equal. So we look at AE and EB. Those are the two segments of my first chord. And then it says the product of those lengths. So we're going to multiply them together. So AE times EB should be equal to the product of the segments of your other chord. So CE times ED. And that's our chord theorem. So let's see if we can use this chord theorem to help us with these next two examples. So here we're asked to find x. So again, we have two chords that intersect inside the circle. So the product of 6 and x should equal the product of 9 and 8. So we can set up our equation. 6 times x equals 9 times 8. 6 times x equals 72. So x equals 12. Okay, let's look at example 2. So example 2 says if AD is 12, find the value of x. So if we know that the length of AD is 12, that's the total, we can find the length of ED by doing 12 minus 3, so we know that ED should be 9. So you do have to do a little bit of extra thinking to figure that one segment out. But now we can use the chord theorem, and we can say 3 times 9 equals 14 times x. So 27 equals 14x. So x equals 27 over 14. Okay, so now we're going to learn about a new type of segment called a secant. So a secant is any line that intersects a circle at exactly 2 points. So it's 2 points instead of 1 point like a tangent. So a secant segment is a part of a secant line with at least 1 point on the circle. So here in the image below, you can see that we have a secant here. AE is the secant because it crosses at 2 points. And we also have CE is a secant because it crosses at 2 points. So the secant product theorem says if two secants intersect on the exterior of a circle, like they do here, these two secants intersect at point E, then the product of the lengths of one secant and its external segment equals the products of the length of the other secant and its external segment. So this one's a little bit trickier to interpret. So the way I like to think of it is I say total secant times outside secant, so outside segment. So the total segment up here would be AE. And again, we're doing the product. So AE times the exterior segment, BE, equals total segment, CE, times the exterior portion, DE. And that's how we would use our secant product theorem. So it's total times outer portion, total times outer portion. Okay, so let's see if we can use that to help us find x in this example 3. So here we can see that we have two secants. So remember, we're going to do total times outside equals total times outside. So here we can say the total would be 8 plus 6, which is 14, times the external segment, which is 6, Now for this other one, you have to be careful because our total is actually the sum of the two parts. So our total here is x plus 7 times the outer portion, which is 7. Okay, so now that we've used the secant product theorem to help us set up our equation, now we just need to solve for x. So here, if I do 14 times 6, it's 84 equals 7 times x plus 7. So we have two options. We could distribute the 7, or I notice that this side is actually divisible by 7, so it might be easier for us just to divide both sides by 7. And then all we have to do is subtract 7, and we get x equals 5. So again, remember, it's total secant times external secant, or external portion, total times external. All right, let's see if we can do the same for number 4. So again, we're going to do total times external equals total times external, and then solve for x. So our total for secant LH would be 4 plus 6, which is 10, times the external portion, which is 6. And then for secant LN, the total is 5 plus x, which would be 2x plus 5 times 5. So here we get 60 equals 5 times 2x plus 5. And again, we could absolutely distribute the 5 to the 2x and the 5, but since we notice that both sides are actually divisible by 5, we can just divide by 5 from the get-go, and we get 12 equals 2x plus 5, and then we can subtract 5, so 7 equals 2x, x equals 7 halves, or 3.5. Okay, the last theorem we're going to talk about is what's called the secant tangent product theorem. So here we have a secant and a tangent that intersect on the exterior of the circle. So for this one, it says the product of the lengths of the secant segment and its external segment. So that's the same as before. We're going to do total secant times outer secant portion should equal the length of the tangent segment squared. So again, that would be AC, the total segment, or the total secant, times the outer portion of the secant, equals, well, we can think of this as the total tangent, which is CD, times the outer portion of the tangent, which is also CD, which is why it's CD squared. It's the tangent of the segment squared. So we can still kind of apply that same rule as the last example, but we just need to realize that for a tangent, the total and the outer portion are the same. Okay, so for example 5, let's see if we can use a secant tangent product to help us find x. So here, again, we're going to do the total of our secant BD. So the total is 2 plus x. Remember, we have to take the sum of the two smaller segments, times the external portion, so times 2, equals 5 squared, the tangent segment squared. So here we have 2 times x plus 2 equals 25. Since 25 is not divisible by 2, I'm going to distribute it instead of dividing both sides. So we get 2x plus 4 equals 25. 2x equals 21. So x equals 21 halves. And we're all done. Okay, let's look at this last example together. So this says, on a bird watching trip, you travel along a path tangent to a circular pond. So here's our pond, and here's our tangent portion. Let's see, I'll highlight it in red. Here's the entire path. And again, we know this is the tangent line because it's only intersecting our pond at one point. And you're taking this path to a lookout station that faces a hawk's nest. Given the measurements in the diagram on the bird watching map, how far is the nest from the lookout station. So we want to find this total length. So you'll notice that here we actually have a secant line. So here we have a tangent right here, and then here we have a secant. So we can use our secant tangent product theorem. So again, we're going to do the total length of our secant, which is labeled as x, times the outer portion of our secant, which is 25, equals our tangent length squared. So that gives us 25x equals 10,000, and that leaves us with x equals 400. So that means that the nest is 400 yards. We'll want to make sure to include the units in our final answer. 400 yards to the lookout station. All right, that is all for today's video. Thank you so much for watching.